Good evening. Welcome to I think it's our fourth Cary Science Conversation. Because so many of you are people who don't know us, and I see names, I just was scrolling through the several hundred names already signed into this seminar. I'll give you a little bit of a history about what Cary Institute of Ecosystems is and what we do. So we are located in Millbrook, New York. We have a 2,000-acre research campus which is mostly recovering northeastern forest. We have been in business for over 35 years, and we study ecological phenomena on a very large scale. I like to say that the work we do really tries to answer important questions that are not just important to science, although that is our first driver, but important to society. We work on issues related to freshwater ecology, forest ecology, both temperate and tropical now, disease ecology, which we'll talk more about tonight, and urban ecology. We do a lot of work on climate change, but I'm of the mind that if you're an ecologist in the 21st century and you study things at a scale greater than 1 meter squared, you're likely looking at the impacts of climate change in one way or another, whether that's increased snowstorms or increased sea levels or floods or droughts or fires. And we study many of those things. So we are independent. We are not part of any university. And we have been doing seminars like this and lectures for many years. We have a series on our campus in Millbrook, about 125 people in our auditorium on Friday nights called Friday Night at the Cary. A couple of years ago, we started doing work doing a seminar, sorry, my language is all virtual now, seminars at WNYC's Green Space in New York City. But this is the first year we've done a virtual webinar and a seminar that is open to all. And it's really remarkable to see the diversity of people coming in. And I'm really glad that you have found out about us through so many different, I'm looking through so many different avenues or channels. And so it is my pleasure tonight to be talking about the ecological and biodiversity basis of pandemics and why those things matter. We are very lucky tonight to have two very distinguished speakers or panelists or conversationalists, I think is probably what we are. First, I'd like to introduce Rick Ostfeld. Rick is a distinguished senior scientist at the Cary Institute. He is a disease ecologist and is someone who knows an awful lot about mice, acorns, and Lyme disease, as does Felicia Keesing, who is the Rose Distinguished Professor at Bard, and we are proud an adjunct scientist at the Cary Institute. Felicia and Rick have done a lot of work together. They are in the same pod, as it were, which is why they are sitting right next to each other without masks on tonight. And both of them are disease ecologists, which is a field that was relatively unknown 15, 20, 30 years ago, but has been accelerating, not just because of this pandemic, but because of the broader interest in the world and in disease more generally and the ecological basis for disease. So having introduced Rick and Felicia and having told you a little bit about Cary Institute, let's jump in. I just want to give one more little background piece. Rick and Felicia, for the last 5 years, have been running something they call the Tick Project. It's an $8.8 million project with a single aim to discover whether we can kill enough ticks to limit Lyme and other tick-borne disease. They are in the final stages of that project, and we hope to have an answer sometime either this winter or next spring. And when we have analyzed the data and they're unblinded, it's a double-blind controlled study. It's why it's so expensive. But when it's all done, I am sure we will lure them back for another Cary Science Conversation, and we will certainly let you know about that. But tonight, let's talk about something different. Let's talk about why does biodiversity matter when we're trying to prevent the next pandemic. You know, I think probably the best first question I could ask both of you is, what is a disease ecologist?
Well, you're looking at two of them, as Josh said, so that's a start. As Josh said, disease ecology is a relatively new subdiscipline within the broader discipline of ecology. You know, it got its start a few decades ago, but really has accelerated dramatically in the past 20 or 30 years. And I think it's widely considered one of the more dynamic, exciting aspects of ecology broadly. It used to be the case that infectious disease was the purview almost entirely of biomedical specialists. That you need to ask the question, if someone is suffering from an infectious disease, what is the creature that is making them sick? How do we diagnose it and make sure we're right? And then how do we treat it? And this is all obviously immensely important, but it's not the whole picture. And disease ecologists are very interested in asking, going further back, that case of disease, the state of ill health, is the culmination of often a very intricate set of interactions that go on in nature, in houses, in cities, in agricultural fields, and elsewhere. And disease ecologists are interested in, where did that pathogen that causes the disease in the person, where did it come from? How did it get there? How long has it been there? How did it get from that source to the human victim? And of course, disease ecologists look at diseases of plants and various other animals as well. So that's a brief thumbnail of our discipline, and you might imagine there are lots of questions that remain to be addressed and lots of current topical importance of that discipline.
I would just jump in to add that I'm a professor and I see a lot of students interested in disease ecology. I think because it blends two things that they're interested in and they thought they would have to choose between, which is health or public health and the environment. And when they realize that there's a way that you could actually study both of those things, or possibly wildlife health and the environment, that makes them realize that this might be a discipline that they want to invest in.
That would have nothing to do with the project you did out in Kenya where your students really wanted to go to East Africa.
Well, dangling an East Africa carrot is a nice thing for an undergraduate too.
It's always a good thing to do. We talked a bit about, we mentioned different kinds of diseases and the ecology of the way in which ecology informs not how to cure the disease, but how the disease came to be and where it came from. And one of the major pathways is through zoonotic diseases. And I was wondering, given that so many of the diseases we look at are zoonotic, could you sort of define what zoonotic means and how common they are?
Yeah, zoonotic disease is the hint. There's a hint in the name with the zoo beginning. That's indicating that it has to do with animals. And a zoonotic disease is a disease that's caused by a pathogen that's transmitted between humans and vertebrate animals. So mammals, birds in particular, but it could be other kinds of vertebrates as well. And the important thing to keep in mind here is that a zoonotic disease could come from an animal to people. It could jump from an animal to people, but it can also go from people to another species. So that's what we're trying to indicate here on the slide that you can see. The animals on the left could be a source of, for example, some kind of virus that jumps to humans, but humans could also transmit that to other wildlife. And we know that depending on what particular time frame you described, roughly 3/4 of emerging infectious diseases of humans are caused by these zoonotic diseases. So they're really important, and they connect us to animals in two directions. It's worth maybe saying that when we want to know where a zoonotic disease came from, the way people typically do that is they go out and they sample a bunch of species that they think could be the source. So again, if we look at the species on the left, you might go out and sample some mice or some monkeys or some agricultural animals and look for viruses, for example, if whatever it is caused by a virus, look for viruses that those species are carrying. And we look for genetic matches between the viruses that are found in those animals we've sampled and the virus that's infecting people. And if we find a virus that has 100% match with people, then we might infer from that species must be the one that gave the virus to us. And I say all this because it's really important to recognize that if we gave the virus to another species, it would also have a 100% genetic match. And in fact, that's what we see with the virus that causes COVID-19. The virus is called SARS-CoV-2. We have a lot of animals now that have 100% genetic match with the virus we're carrying, but every single one of those species got it from us. We have not found the one that gave it to us. And at this point, that might be very difficult to do, but we know that we can give it to a lot of other species, and we already have.
Let me just jump in, just Josh, sorry to interrupt, but we have the term emerging infectious disease up there, and I just thought I would provide very briefly a definition for what that means. There are various infectious diseases like colds and staph infections and things like that that aren't considered in that category of emerging infectious diseases. These emerging ones are defined that way on the basis of either being something that's brand new, it's just discovered, never known to exist before, the pathogen that is, or it suddenly gets much, much worse than it was, or it suddenly expands its geographic range dramatically, like jumping an ocean or moving globally from a local area.
Or all three at once, as in the case of
Sometimes it doesn't.
As is the case, yeah. And you know, I think that's important because, you know, there are diseases that are zoonotic that we have been dealing with for decades or centuries or millennia. And so zoonotic diseases in and of themselves are not emerging. But I think one of the questions for tonight that we'll get to in a little bit is, so why now 75% of emerging infectious diseases are zoonotic, so why now? And one way to ask that is, Felicia, you mentioned that, you know, if we look at the tigers at the Bronx Zoo and we do their, sequence the SARS-CoV-2 that they had, and we find, lo and behold, it's identical to that which their keeper had, then we know that we've given the tiger COVID-19. So what about the other direction? Why, you said it was so hard, where did COVID-19 come from, and why is it so hard to find out where it came from?
Well, so the first part, where it came from, we are confident that it's a zoonotic disease because it's closely related to SARS-CoV-1, which that's why it's called, the virus that causes COVID-19 is SARS-CoV-2. It's so similar that we've named it with just a second version or a second type of this virus, this larger group of viruses. And that one is zoonotic as well. So we're confident that it's a zoonotic pathogen, but we've never found the host that it comes from definitively. What you may have heard that it's bats or that it's pangolins, a particular kind of scaly anteater-like mammal. Those are just the closest of the ones we found. So, you know, if you find a bat that has 96% sequence similarity of its viruses to the virus that we have, and that's the closest you have, then it's reasonable, I suppose, to infer that that bat must have the ancestor of the virus we have. But that's not actually saying that that bat was the source of this virus. It's just saying of the animals we've sampled that could have been the source, the bat is the closest. But it could be something else entirely, and we simply don't know. And why that's difficult is because we have to find the species that has it, but we actually have to find the individuals of that species that are carrying it. And so you might sample a particular kind of primate and not find the virus in it and infer that that this primate couldn't be the source because it doesn't have the virus. But if you'd sampled a different individual, you might have actually found the virus. So it's a really large sampling problem.
And can we assume that the longer we don't find a very close match in an animal, that this virus mutates, and therefore there will be divergence both in what we're carrying and what they have? And so that there is a time, you know, as it were, you know, if we want to find the culprit, time is of the essence?
Well, I mean, I don't think we're worried about a few months or even a few years. So the SARS coronavirus 2 is mutating. Molecular biologists have detected some changes in the nucleic acid sequence of the virus, but they tend to be very small in magnitude compared to what separates SARS-CoV-2 from, for instance, SARS-CoV-1 or other coronaviruses. And there are quite a number of other coronaviruses. So yes, we don't want to waste any time, but I'm not that worried that if it takes another few months or even a few years, that it will have changed so radically that we won't recognize the original virus if we find it.
Right. Okay. Let's switch gears a little bit. You know, I read something recently that said we are all epidemiologists now, right? And you know, there's nothing like a good pandemic to get the general public to understand things like the concept of R sub naught, or the intrinsic rate of increase of a disease. But you know, we know that we've learned a lot as a society about COVID-19. But how does it compare to other zoonotic diseases, both in terms of the route of transmission, the level of mortality, how many people have been infected? You know, what have we learned from other systems that would allow us to put this pandemic in comparison?
Yeah.
Let me start, and then I'll turn it over to Felicia. So one way in which SARS coronavirus 2 is different from many other zoonotic pathogens, although not all others, is that it is easily transmissible from person to person. So I think we're going to be talking more about other zoonotic diseases in a few minutes, but most zoonotic diseases, you have transmission events from the animal reservoir host, the host in nature or it's somewhere in the environment. And every time a person gets sick, that is because they had that pathogen transmitted to them from the animal host, not from another person sick with that virus or that other pathogen. Only in a few cases, once a person gets sick, can they then onwardly transmit the pathogen to other people. And this is one of the ways in which this COVID pandemic is so fundamentally different from so many other zoonotic diseases, of which there are so many, and there's such a high burden of disease all over the world with them.
Yeah, so that's one way of thinking, you know, what's different about this one. It's not unique in this way that Rick described, but it does make it in a particular subset of zoonotic diseases. Another way we could look at this is to think about the kinds of things you mentioned, like how transmissible is it? How infectious is it? What are the basic epidemiological characteristics of this virus? And I would say there's no individual characteristic of this virus that is incredibly fancy or special or unique. It's not more infectious than other things. There are other viruses, other pathogens that are much more infectious. There are other pathogens that have a higher fatality rate. So there's no single characteristic, but the suite of characteristics altogether of this virus is what I call kind of the perfect storm virus, right? It's got a particular set of characteristics altogether that make it particularly hard to combat. And one of the most important of those is that people, as everyone now knows, people can transmit before they know they're infected. And so that, again, that's not unique. The influenza virus that causes seasonal flu does that too. And it's one of the reasons that we get it every year. And the flu is so infectious because of that. And so is COVID for the same reason. And so again, I think it's this constellation of things, but when we compare it to, we've mentioned SARS-CoV-1 that caused severe acute respiratory syndrome. With that disease that swept around the world and it hit the United States, in fact, 20 years ago, the big difference was, well, one of the big differences was that people didn't transmit SARS-CoV-1 virus before they had symptoms. In fact, they usually had symptoms for about 10 days or 2 weeks by the time they started transmitting. And at that point, they were so ill that they were in the hospital. So we didn't have this kind of community transmission that is what we're all battling in our workplaces, our schools, our grocery stores, our restaurants, because people were already hospitalized. And so the outbreaks for SARS caused by SARS-CoV-1 tended to be in hospitals, but that allowed it to be somewhat more self-contained.
Muted. That then, you know, allows us to understand why this is a pandemic, rather than So, and you know, malaria, which has what, 200 million cases a year. It's a horrible disease. I know from it personally. And nonetheless, every one of those was caused by being bitten by a mosquito that was infected, right? As opposed to you go to the supermarket and somebody coughs on you and you know, all of a sudden you're spreading the disease. So this is spread much more quickly than many non-communicable diseases from people.
Right. So if we look at the graphic on the slide, we're approaching 1 million deaths from COVID-19 in 9 months.
Yeah.
That's really an extraordinary rate, and some of that's, you know, all these things we've talked about, including the fact that we now understand that the virus is transmitted quite readily in an airborne way, right, as aerosols, which is really frightening. And so you know, again, it's not unique in that way, but it does have this perfect storm of traits that has led us to 32 million documented cases and almost 1 million deaths globally.
And you know, there's a new podcast on how we should have actually known about 9/11. And if you go back and even read the popular literature, you know, David Quammen wrote a book called Spillover, a decade ago. There have been a number of movies. This is not something that we have not thought about previously. Can you talk a little bit about the other zoonotic diseases, some which may be sort of pandemic like or not, but why they haven't, you know, captured, well, number one, why haven't they become pandemics? Number two, why haven't they sort of provided that warning signal that we really would like?
Well, so the list of zoonotic diseases is very long, and there's a selection of them put up on the slide that I hope folks can see. Here in our neck of the woods, here in the northeastern US, Lyme disease and other tick-borne diseases are very important and very widespread zoonotic diseases. The pathogen, in this case a bacterium, comes from animal hosts, particularly small rodents, things like white-footed mice and chipmunks, and then gets transmitted to us by the bite of a tick. So it's a vector-borne disease. That is also true of Chagas disease, in which the vector is a kissing bug, an insect, and in leishmaniasis, where the vector is one of a number of different sandflies. And the pathogens are different in the case of Lyme disease, but those three are considered vector-borne diseases. So in each case, when a human gets sick, they were exposed when that tick or that sandfly or that kissing bug bit them. And then they do not transmit that infection onto any other people, typically. The other three diseases up there are transmitted without a vector. They have various different modes. Leptospirosis comes typically from contaminated water. Also, again, small rodents are the main reservoir host, the place where that bacterium proliferates and thrives. The same is true of hantaviruses, although that is also airborne. And Ebola, which I think many people know about, caused by Ebola virus, can be transmitted from person to person following exposure. And the original transmission from wildlife hosts, in this case apes, was relatively unimportant. I mean, it was important in giving rise to later transmission, but most of the human cases of Ebola are experienced by people transmitting it to one another. So the total burden, health burden of zoonotic diseases worldwide is enormous. As I've mentioned a couple times, I think by now, most of them are not transmitted between people. And so they don't typically move into pandemic stage, pandemic category, but not much really does. I think the COVID pandemic is perhaps not unprecedented, but at least in the past century or so, it is, in the sense of how many cases there have been, how quickly and with what impact on human health and well-being and livelihoods.
I want to respond to the other part of your question, Josh, where you're saying, you know, why didn't these serve as a warning signal, and why didn't we act on these when we've seen these zoonoses? I mean, there have been very, very concrete predictions over the last decade in particular about the potential for something like this to happen, and people have done scenario building and that kind of thing around it. I think it was something that policymakers and to some extent the public didn't take as seriously as they should have, and this is where we are. But I particularly want to focus on the second part of what you said, which is that, you know, why didn't we act after we'd seen these kinds of zoonotic diseases? Why didn't we act within our countries, for example, to prepare for them? And the fact is that some countries did. So I did an interesting sort of quick analysis early on because there were such varying rates of spread of COVID in different countries. And it turned out that the countries that I looked at that had experienced SARS caused by SARS-CoV-1, I just looked at those countries and I asked which of those countries had implemented public health interventions as a result of their experience with SARS, the first version, and which ones hadn't. And it dramatically explained the difference between the growth rates of the viruses. So a lot of countries in Asia in particular that were smart about it and learned from their experience with SARS implemented practices about how they managed intakes in hospitals, for example. And of course, the use of face masks became much more widespread after SARS the first time around. And we didn't do that in the United States. Canada didn't do that. A lot of countries didn't do that and saw these very rapid growth in cases. So it is possible to learn, and part of what motivates us to do things like this event and many others that we've been doing over the last few months is because we hope that all of us will learn more as a result of this so that we start making the right choices and we never have to live through a situation like this again.
All right, so I'm going to shift gears a little bit and get more closer to the topics, the topic of the advertised topic for this talk. You know, you both mentioned various critters and insects that, you know, kissing bugs giving you something nasty. That's really, get my head around it. But you've mentioned biodiversity as the vector and as the host and as the reservoir for these diseases. Does that mean that the summary of why biodiversity matters to pandemics is biodiversity is dangerous?
Yeah, I think a lot of people have gotten that impression, right? If we could get some new pathogen from any different kind of, you know, vertebrate animal out there, like any of these beautiful animals out in this East African savanna, then that would suggest that biodiversity is dangerous to us. If they're all equally likely to give it to us, then why would we want all these crazy kinds of things around spreading pathogens? And if that were the case, then biodiversity would be a hazard because it's a source for all of these different pathogens. And so one of the main points that I want to make, and I think Rick do tonight, is that those species are not all equally likely to share pathogens with us. Some of them are far more likely than others. And in fact, the most likely species to share pathogens with us, you can't even see in that slide. In fact, as Rick likes to say, you're far more likely to get the next emerging infectious disease from a rat than from a rhino. And I'm going to let Rick explain his favorite statement there.
Yeah, I guess, you know, one thing, it's important to realize that in that savanna picture, all those animals were carrying their own pathogens. Animals just do that. Pathogens do that. They're really good at making a living inside the bodies of animals. And a superficial understanding of that would suggest that each critter then is equally likely to be the one that harbors that next pathogen that's going to make the jump to us and make us sick. And as Felicia has emphasized, the scientific evidence indicates very clearly that that's not the case. So I don't want to start going back through the slides, but when we talked about these other very important zoonotic diseases worldwide, Chagas disease, leishmaniasis, Lyme, and the other tick-borne diseases, all the hantaviruses, those come predominantly from small mammals, especially rodents, sometimes small marsupials that kind of look and act like rodents. And it turns out that if you look through and classify all the mammals by the order in which, the taxonomic order in which they occur, and you start to ask, well, which are the most important in producing the zoonotic pathogens that make people sick? By and large, you come up with rodents as the most important group of mammals. Depending on how you measure importance, sometimes it's also the carnivores, the dog and cat family of mammals. Occasionally, it's the hoofed mammals that are seen as most important. This depends on what you're counting exactly and how you're defining importance. But by and large, the total number of zoonotic pathogens coming from rodents is higher than the total number coming from any of those other groups.
By a lot.
By a considerable margin. So that indicates very clearly that the total aggregate of biodiversity is not in and of itself a threat. It is only certain specific components of that biodiversity that constitute a threat of some kind of spillover, either through a vector or to us or directly to us.
And there are certain traits that make something likely to be a zoonotic host. So that's true even within the rodents. Our colleague at the Cary Institute, Barbara Hahn, has looked at all rodents and asked, of the ones that are the sources of zoonotic pathogens, hosts for zoonotic pathogens, what characteristics do they have that differentiate them from the traits of the ones that don't give us pathogens? The traits of the ones that do give us pathogens, the dangerous ones, is that they have a large geographic range. So they live across a large area. And then they tend to have a suite of characteristics that we think of as sort of live fast, die young, right? They tend to have small body size, reach reproductive maturity very early in their lives, sometimes weeks, possibly a little bit longer than that. And then they have a lot of offspring and everyone go, and they just don't live very long. So those are the traits captured by, if you look at the left-hand side of the slide, that's a zoonotic host, right? Those are the ones that tend to give us pathogens. But if we look over on the right and look at the rhino, what are the traits of species like rhinos that, are they the traits like that? No, they're not. Rhinos tend to live are over a smaller geographic range, and they tend to have large body sizes and live for a long period of time and have few offspring. And it's the rhinos and things like that that are vulnerable to extinction. When biodiversity is lost, we lose the rhinos. We don't lose the rats. In fact, the zoonotic hosts, it turns out, thrive when we lose diversity. So if we go back to the slide of the African savanna, and we think about, is it all of those hosts? No, is it all of those species? No, it's not. It's actually the biodiversity represented in that image is actually protecting us from an increase in the zoonotic hosts that would thrive in the absence of those larger species.
So I think, yeah, Rick.
I was just going to say, because that beautiful picture of the savannah is before us. Josh mentioned that Felicia had spent some time in Kenya looking at scenes just like that, and her research basically focused on the things that you can't see in that slide because they're too small, they're hidden in the grass. Basically those are these rodents, these various kinds of rats we're talking about, and other small mammals. And what Felicia found is that when you have a scene like in that slide where there's a large biomass and a large diversity of large mammals, these being the ones that tend not to transmit pathogens to us, they tend not to be good zoonotic hosts, then there aren't that many rodents in the grass. They are inhibited by competition, possibly by trampling, by other ecological phenomena. But when those larger things decline or are experimentally excluded, otherwise disappear, then the rodents have a field day, a savanna day, I guess, and they start to proliferate very rapidly. And as they increase in abundance, so too does the transmission potential for the pathogens that reside within them.
So what you're saying, if I get it right, is that it's not that biodiversity is dangerous. And in fact, it's only very particular parts of an ecosystem or members of that community that present a threat to humans, but that unfortunately, because of their live fast, die young, leave lots of kids, approach to life, they're the ones who don't go extinct. They're the ones who can survive human interference just fine. And that even worse, by killing off other species and reducing the diversity in an ecosystem, we may well be increasing our disease risk by opening up space for the things that can deal with the disease and pass it on to us. Is that a reasonable summary of everything you just said?
That's it exactly.
Yes,
Right.
and there are some recently published studies that have, by independent laboratories in the United States and in the UK, that have done a global analysis to ask what happens to the mammal and bird fauna as we move along a gradient from undisturbed natural habitat, like in that savanna slide, into a greater and greater degree of human disturbance. So including agricultural, land use changes, suburbanization, urbanization, and the like. And what happens when you move along that gradient is you're actually imposing this giant filter, is the way I like to think of it in metaphorical terms. You are making things really difficult for the big, long-lived, live long, die old kind of species, the ones that either are unimportant in transmitting pathogens to us or are actually serving a protective role by inhibiting the good reservoir species. So those are the ones that don't get through the filter. The ones that do get through the filter are the little guys that live fast and die young, that move around a lot, that actually even occupy some of our human structures sometimes. Those are the ones that has been now well demonstrated that are much more likely to harbor these zoonotic pathogens. So inadvertently, when we are converting the landscape to other uses such that biodiversity, the overall diversity, is lost, we are unintentionally increasing our risk of exposure to these zoonotic pathogens.
Right, and that's a twofold process. I want to ask, sort of close up before we take questions. I want to sort of do a two-pronged question. I think there are two slides, which will help. The first of which is, okay, what's causing what's driving the biodiversity loss? You mentioned some factors of urbanization and suburbanization, and then if we know those factors, are there actions that we living in the United States, or we have some people from South America, but what are the things that we can do personally in our lives that may reduce the pressures on land and therefore reduce the process of extinction and biodiversity loss? So let's start with what are the real risk factors that are not just leading to biodiversity loss, but also getting us in closer contact with these animals?
Yeah, so the major forces are on the slide, right? So we see biodiversity decline as a result of habitats being converted from particularly their pristine state into the kinds of systems that Rick talked about, agricultural systems or other kinds of managed systems or urban or suburban environments. We also see that harvesting, so here we're thinking hunting, but also harvesting for the wildlife trade for other reasons, and leads to loss of biodiversity. So that could be for the horns of rhinos, for example, or the scales of pangolins, but also for food. And then climate change is a huge driver, and so is pollution, and pollution of all kinds, not just plastics pollution and garbage, but also toxic pollution. So, and in fact, we could think of climate change as a kind of carbon pollution. So what we're saying is that all of those things that damage the environment in other ways as well lead to loss of biodiversity. And what we're emphasizing tonight is that the most competent hosts for zoonotic pathogens are the ones that are going to thrive when biodiversity declines as a result of these forces.
Okay, and I think we have over the years had many lectures at Cary on the issue of biodiversity loss, and I think people have read the Sixth Extinction and other wonderful resources. Let's go on just to close on things people can do, and I know that one of those things is going to be up on the screen any moment now. is to eat fewer animal products. As vegetarians, you guys can sit on the high ground here and talk to us about why that's important. Why is it important to reduce carbon and other actions we can take?
I want to step in and say that I think that we should reduce our use of animal products, but we would never lead that by saying we're vegetarians, because we're not actually advocating that everyone become a vegetarian. We just think it's environmentally responsible to eat fewer animal products, but that just means cutting back from where you are, because that's a driver of the drivers of biodiversity loss. It leads to habitat conversion and all of those kinds of things.
Right.
I think a broader issue is that, there are many justifications, rationales for being better stewards of the environment. They sometimes refer to human welfare. Sometimes they refer to the sort of a moral or ethical imperative that we have to be better stewards of our environment. I think that one of the things, to come full circle, that disease ecologists are now showing is that a healthy environment, a better preserved, more intact, more biodiverse, less polluted environment will in many cases protect us against infectious disease. It protects our health in other ways as well, including psychological health, including better nutrition, including less likelihood of dying from excessive heat or fires that can kill people immediately and then reduce the quality of life for the very long term in that region and actually elsewhere. So the potential for environmental protection to be a win-win, in the sense that there's a co-benefit obviously for environmental health, and perhaps less obviously, but it should be obvious now for human health as well. And so that's why consuming fewer animal products is important, because it reduces carbon emissions, among various other things. It reduces excessive use of water and land. And as we've pointed out, all these things have an impact on biodiversity, both locally and globally.
Right. And go ahead, Felicia.
Well, I was just going to say that there's sort of a step missing in between, that if we want to protect biodiversity or address the biodiversity relationship with infectious diseases and zoonoses in particular, what we're ultimately trying to do is to protect, preserve, and restore biodiversity, right? And so we're saying, if you want to do that, here are a suite of things that address, reduce pollution, reduce climate change, et cetera. But the things on this slide are some of those, the factors roles that you could play that would help protect, preserve, and restore biodiversity while also having these other benefits. And those of us who are in the United States and able to vote have a chance to make our voices heard very shortly. And this is a really pivotal election in the United States for thinking about whether we want to have science and science-based decision-making playing a role as we go forward and rebuild. The sort of build back better theme, I think, is important to bring in here. We are going to need to rebuild our economy in different ways, our energy infrastructure, our employment infrastructure, our health infrastructure, and our environmental infrastructure as we come back from this. And informed, if we're wise, informed by this experience, we can do a better job so that we make this less likely to ever happen again. And so I would encourage everyone in this country who has the power to vote to use it. And those of you, I know there are people from around the world, which is delightful to see. Those of you who have votes as an option in choosing your government, again, I couldn't encourage you more strongly to use your voice, use your vote. Right.
And I really appreciate the use your voice and supporting science. I mean, I remember 4 years ago when there was the first March for Science, thinking it was a really bizarre thing, because as somebody who had been in the field for 30 years, I had never thought that I would have to march for science. I think many of us as scientists, and many of the people on this webinar who obviously are interested in science, can't quite believe that we're not actually using science to the best of our abilities. Now, we all know that science is but one part of good policymaking. There's economics, there's social issues, there are many things that go into it, but I think what we are seeing and what Rick and Felicia have done such a great job of showing us is that it's not a lack of knowledge per se that is causing the spillover and the potential for pandemics, and in this case, the SARS-CoV-2 spread and pandemic of COVID-19. It is our not focusing the science on management and policy soon enough. And as Felicia said, many countries who had to deal with SARS learned from it and did a better job with SARS-CoV-2 or COVID-19. So this is really important stuff. Thank you so much. We got a whole bunch of questions here. And I'm going to look through the Q&A, and we can start answering some question. So here's an interesting one. Has anyone calculated the total economic cost of zoonotic disease? Because obviously one of the things that people say is it's very expensive to prevent these things to begin with, and obviously SARS-CoV-2 and the COVID-19 pandemic is really clear how expensive it is not to deal with these things. But do we have an idea of the sort of economic cost of zoonotic disease overall?
That's a tough one, because you'd have to draw your boundaries. It's a great question. You'd have to draw your boundaries around over what time period, because there are zoonotic diseases that are, as Rick said, that have been with us for a long time. So for example, the plague and tuberculosis are both zoonotic, and so is smallpox. And trying to calculate what the economic cost, if we included that, that long time lens, that would be a really incredible challenge. It would be fascinating, right? And it would probably end up being a major chunk of human economic productivity over our history. But you'd probably want to limit that to a smaller time span, like let's say since 1950 or something like that. And I don't know of anyone who's done it. There was a paper that came out in Science magazine about a month or 6 weeks ago, in which they estimated the economic cost of COVID versus what it would cost to do the kind of monitoring and surveillance that the authors argued would prevent the next COVID pandemic, or the next pandemic like COVID. And they came out with the cost of preventing the next one in the way they saw that happening was trivial compared to the cost of this one, and that was the case that they were trying to make. But I don't know anyone who's tried to do it over a suite of diseases.
And I think it would be very difficult. I'm not an economist and would never pretend to be, but I think that deciding what costs one would want to include in such a calculation would be challenging as well. So for instance, just with Lyme disease in the United States, the total healthcare costs of Lyme disease have been estimated with wide margin of error. It's something like $1 billion in this country alone. But that doesn't include any of the missed recreational opportunities, the impact on property values, on other ancillary kinds of industries that occur in and around the Lyme disease endemic zone. So there are the obvious costs in the sense of healthcare, but then there are a lot of less obvious costs that are much harder to estimate. And to do that across zoonoses across the world, I think would be a major challenge. Sure would be for me as a scientist, not an economist.
I'm just looking at another question. So here's one from somebody in high school, Evan, who's from Cary High School. How appropriate! It's North Carolina, Cary, but we'll take it as fandom. He's wondering if there are any non-anthropogenic disturbances that decrease biodiversity, right? So are human-driven processes the major thing, or there are other things, whether we call them natural or otherwise that
yeah, that's a fantastic one. I mean, of course there are, and we Californians lived this in vivid. Californians, people along the West Coast of the United States have been living this for weeks now. Wildfires would be absolutely one of them. And so would things like volcanic activity and things like that. So lots of what we call abiotic, non-living forces can affect biodiversity as well.
Yeah, and I don't know if Evan has taken earth science in high school yet, but there are multiple examples of mass extinction events that have occurred periodically throughout the entire Earth history. So there certainly are non-human caused reductions, often massive reductions in biodiversity. Those are not so much in our control. An asteroid, good luck.
Well, we'll worry about asteroids.
I wouldn't put it past 2020 at this point, but
I'm very glad the Jewish New Year started last week. All right, it's at least we can believe
Move
that
on
we're
to the next year.
Somebody mentioned that there is a One Health bill in Congress that's in committee that is being supported by a bunch of veterinarians, many of whom I think we know. And I was wondering whether Katie's wondering whether you might comment on sort of how ecologists feel about the One Health concept.
Oh, this is all you.
Well, so I think there's generally quite a bit of support among ecologists for the One Health concept. My understanding from having been to One Health scientific meetings is that the predominant scientific discipline would be veterinarians, but there are environmental scientists, there are actually physicians who are proponents of the One Health concept.
Could you just mention what that is for anyone who's
It's so One Health is the notion that animal health, human health, and environmental health are inextricably linked. I think it can be extracted into a statement like that. And that is certainly demonstrably the case in many instances. I think ecologists are often interested in the specifics of how one might define environmental health. And that becomes important. That's not just a semantic issue. There are various ways of defining what that means, as is true for human health and animal health as well. Are we talking about individuals, populations, entire communities, and the like? But I think that the embedding of the health sciences, veterinary medical sciences, within the broader rubric of the determinants of that health from outside, from a greater distance, and especially in the context of zoonoses, which that's the context I'm thinking about, from animals that live in habitats that can be affected by us. I think there's a lot of sympathy for that point of view. And there are ecologists, myself among them, who attend some of these One Health meetings. I'm not familiar with this bill. I will look it up when we're finished. I'm quite interested in it, but I do think it's a promising area. And there are other similar movements, disciplines. There's planetary health, which now has a brand new textbook. There is global health.
And conservation medicine as well.
Conservation medicine, they all have quite a bit of overlap with disease ecology. And I think that's a good thing, that there are a bunch of different groups that are converging on very similar concepts to address similar problems.
Okay, now Lori Quillen, Director of Communications, said that there are a couple people on phones with raised hands. And so what we're going to do is, why don't we try and see, Lori, if we could have Paula Phipps ask her question, see if that works. This is a new trick. Paula, talking's permitted.
But you're muted right now, Paula.
Can you unmute?
There we go.
There we go, Paula.
Okay. Well, I'm wondering why, in terms of the things that one can do, what can one do about things like the mining and the conversion of land to palm oil plantations that's happening so massively in Asia and in Africa? How does that fit into something that one can do? Because those are major impacts on biodiversity loss and ecosystem destruction.
Well,
Thank you, Paul.
it's a great question, and it's absolutely true that mining and certain agricultural practices like palm oil plantations are a potent force that reduces biodiversity and has other environmental impacts. In some of these cases, there are certification programs that tell you where certain products come from and indicate the degree to which those products were produced in an environmentally responsible way. That's one way as a consumer that one can have an impact on some of those practices. There are also reports that can be found about the practices of corporations, and there's increasingly more information on investments that one might make and what are the component parts of those investments, things like mutual funds. So being a discriminating consumer who speaks about one's concerns to one's politicians, to managers of financial issues, and speaks in the aisles of the grocery store. These are at least some things that people can do.
Yeah, I would echo that. The reducing consumption is a really powerful way. So it's hard, even if you're buying well-sourced things, you can be having an impact. So just keeping in mind that the more you cut back and only buy the things that you need, the less environmental impact you're having. I think for people who have the luxury of having investment choices, and that includes through retirement funds and things like that, that's a kind of financial pressure because a lot of those places are supported by investors. A lot of those companies are supported by investors, and we can make noise as shareholders, for example. And again, I'm referring to people who have the luxury of owning that kind of access to financial capital. Right? We have choices about what demands we make on our pension funds, right, on our own investment strategies.
Yeah, and one of the other questions which you've answered now, which is ecosystem restoration to promote biodiversity recovery is a long-term project, and so what can we do? And I think you've answered that, but I also think it's important not to give up on ecosystem restoration. I think that nature recovers pretty quickly if left to her own devices. We need to do, in some places, we need to actively restore. But I think that the power of reduced consumption, the power of cities, right, and living in higher densities may be actually a good thing overall. I think early in the pandemic, people thought, oh God, I never want to live in a city again. But then the disease spread to rural areas, it showed that it was happy to infect people wherever they got close to one another. And it didn't have to be in an urban environment. And in fact, now New York City, which had one of the highest levels of COVID, has one of the lowest. So we can manage it. But I think all these things are important. I was going to ask whether each of you would like to say a couple closing words.
Well, I would just like to maybe point to, this is all can get very grim, especially at the moment in a grim year. And I know we're all wrestling with it. Nobody is having a 2020 that's not impacted by COVID and many of the other issues that have come at us this year that are much on our minds. I want to inject maybe a note of hope following up on what you just said, Josh, that there are things to be hopeful about, including the potential for the environment, for habitats to recover quite quickly. And there is a wonderful national park in Mozambique, for example, called Gorongosa. And there are all kinds of specials you can watch on YouTube, for example, of how Gorongosa has recovered when it was simply sort of set aside and preserved after the end of the Mozambique Civil War, and it's recovered incredibly quickly, and it's really quite heartwarming to see that. And then another example is from a farm in Sussex, I believe, in the UK, where they basically just stopped farming and let things happen there, and they have had an incredible return of a bunch of species that were not found in the UK at all anymore and have migrated over from Europe and colonized the farm. So there are examples of this, and there's lots of potential for us to do this here in the Northeast, and I'm sure in many of the places that the callers from around the world are living in.
Dr. Ostfeld.
Well, I guess I would just like to talk to the students for just a second. I think there are high school, there may be college students, there may be other students as well. And just bring us full circle to say that for any of you who are really interested in studying nature, being a scientist who studies nature, but also have an interest in human welfare, that there are enormous opportunities in the field of ecology that I think we've tried to illustrate the point that the biomedical sciences are just a branch of ecology after all. So even if you go to medical school or dental school or veterinary school, if you study epidemiology, you're studying ecology, and vice versa. If you go out into the field and you become a field biologist, which is an amazing, wonderful, incredible thing to do, you can actually, if you choose to, direct that knowledge that you gain towards the betterment of human health and human welfare. So there really is utility as well as beauty in being an ecologist, and it's a very exciting time in these fields. So I would just encourage the students to keep an open mind and pursue your dreams if they happen to be scientific dreams. And in the field of ecology, that might also mean that you will become interested in great things, creepy crawlies like ticks and mosquitoes, but also the little viruses, bacteria, fungi, and other things that can make us sick, and really understand where they come from, how they operate, and how we can protect ourselves against them.
Well, that's great, Rick. And I think it's the first time I've had somebody on one of these conversations pitch ecology as a future profession. I couldn't agree with you more. I do not regret the almost 40 years I've spent as an ecologist and have really enjoyed my life. Somebody asked what the average day of a disease ecologist looks like, and I'll just summarize it by saying there are no average days.
That's exactly right.
Can I just say though, for the students, Rick was joking to some extent when he said that medicine is a subdiscipline of ecology and epidemiology is. So let's not get the hate mail from the epidemiologists and the public health specialists.
But the two are much more closely related than anybody would ever think.
Absolutely.
So on that
note,
I would like to thank both of you for a wonderful conversation. I would be remiss if I didn't thank Harney and Sons Teas and the Harney family, who have been remarkable supporters of our virtual and our in real life conversations and lectures, and Heather Croner Real Estate, who has not just been a great neighbor, but a fine supporter of our work. So thank you. We really appreciate that 400 people showed up for this. We really would love you to tell your friends about us, and we will be posting this online. I saw one of the comments was not a question, but thank you, this is fantastic. I'm going to tell everybody I know about it. Well, it will be posted. We'll send you an email link, and we'll send you an email with a link to this so you can send it to people. One of the great pleasures of this series, and one of the high points of the pandemic for me, is being able to reach out to so many more people, 3-4 times as many as we would have at a normal seminar or lecture. And so please come back. We will be doing these again. I think they're going to be part of our future, even when there's a vaccine, even when we're back in our beautiful new renovated offices. We are going to be continuing to reach out to all of you, your friends and your family. Stay safe. It's a little bit early, but have a wonderful weekend. And thank you for joining us on this Cary Science Conversation. Bye all.
Bye,
Thank
everyone.
you, everyone.
Thank you for coming.
Thank you, Josh.
Thanks, Josh.
Pleasure.